Hey everyone, and welcome to the internet. What we're going to be doing in today's triple physics lesson is having a look at motors and hopefully learning how they actually work, so you'll be able to explain how a motor works. To start us off, let's see what we can actually remember from before the Easter break. If you're working a target grade up to a grade 5, it's the two questions on the left. For those of you working over a grade 5, it's the questions on the right. So I'm just going to give you about 3 minutes to have a go at those. Write the answers in your book for me. Okay, let's check those answers then. So for those of you doing the up to grade 5 question, then our first one, it will move downwards. So we're going back to Fleming's left hand rule. So left hands, remember, with our wonderful little finger positionings. Now what we need to do is remember, point your first finger from north to south. So your finger should be pointing from the right of the screen towards the left of the screen as we look at it. Then we need to look at which direction the current is flowing in. And in this case, it's flowing from inside the screen towards us. So that means you're going to have to turn your hand upside down so that your finger is pointing out of the screen, as it were. And then look at the direction your thumb is pointing. It's pointing downwards, which means it will move downwards. For question 2, we're going to use our force is magnetic flux density times our current times the length. So 0.5 times 10 times 0.5 gives us an answer of 2.5 newtons. So tick those if you got them right and give yourself a score out of 2. For those of you doing the grade 5 plus, then question 1, it's the same. Okay, it will be downwards, exactly the same way we just worked it out. And then for question 2, it's still using that same equation of force is our magnetic flux density times the current times the length, but you've got slightly more complicated numbers if you like. So our magnetic flux density is 2.4 times 10 to the minus 4. We then need to multiply that by our current in amps. Now I gave it to you in milliamps, so to convert that we've got to do 850 divided by 1000, and then we need to multiply that by the length, and again in the question I gave it to you in centimetres, we need it in metres. So 12 divided by 100 gives us our actual length in metres. Put all that into your calculator and you should get 2.448 times 10 to the minus 5 newtons. So again, add that up, give yourself a score out of 2. Let me know in the chat window who got 1, who got 2. Hopefully no one got 0 today. To start us off today then is a couple of questions that I'd like you to write the answers in your books for me. First one, what can we use robots for? You can give me a lovely bullet point list on anything we can use a robot for. And the second one, how do robots move? So write the answers to those two questions in your book for me. I'll give you a couple of minutes so you can have a go at answering each of them properly. So what I've actually got for you then is a little clip that I found which is looking at how we've used robots very recently in the coronavirus outbreak. So we're actually going to have a little look to see what China was doing in some of their hospitals using robots. So hopefully what you could see in that video then are just a tiny number of uses of robots. Now that's just looking at how some of the countries around the world are actually using robots during this pandemic to try to help things out. So you saw in the video that they've got some of these ultraviolet emitting robots. So they're able to go into rooms and actually disinfect them using these ultraviolet wavelengths that are incredibly harmful to humans. You certainly don't stand in front of those things, but it kills the virus. Now, far better than obviously sending in a cleaning team there. We've also got the ability to use robots to deliver materials to people who are in quarantine. And some of the areas where people were in isolation, then they've used robots to deliver meals to them, for example. Obviously, in everyday life outside of pandemic land, then we use them in a huge number of factories. So gone are the days where there's someone who actually screws the caps onto the little toothpastes and all of this. Now it's done by an actual robot or a machine. So we've used robots in a whole range of places. You may even have robot floor cleaners in your house if you've got the little ones that zip around and do all the hoovering on a timer. You might have ones that mop your floors. Who knows? Robots are everywhere. In terms of how they move, then they use a motor to actually enable their different moving parts to actually do just that, to move. What we did just before the Easter break was we had a little look to see what happens when we place a current carrying piece of wire within a magnetic field. Now hopefully you remember that the current carrying wire will produce its own magnetic field, and then those two fields are going to interact. So what we're going to be looking at today is a loop of wire. So if we take a loop of wire and place it into a magnetic field, then when a current flows through that loop of wire, it will generate its own magnetic field, just like we said previously. Now what we've actually got are two sides then on that loop. So what we then end up with is a force acting on the two different sides in opposite directions. So what we end up seeing happen then is that loop of wire is going to turn. If you look at the picture in the bottom left, you can see our loop of wire within our magnetic field. Now what we can see, there are two red arrows. So the one on the left is pointing up, the one on the right pointing down. So what's actually happening there is because of Fleming's left-hand rule, then what we see is the wire is going to be pushed up on the left-hand side of the coil and down on the right-hand side. So that means the whole loop is then going to be turning. And just to show you what it looks like in terms of our magnetic field lines, if you look at the diagram on the right, then you can see we've got those two catapult fields. So we've got the little circle there representing our actual loop of wire. So one on the left, one on the right for those two parts. Then you can see the circular field lines around each of those, which have been distorted, of course. And we can see the field lines running between the north and the south poles of the magnet, again with that distortion. And remember what we said, those field lines are going to be shortening. So that means that on the left hand side, it's going to be pushing up. So that bit of the wire moves upwards, and on the right hand side it's going to be pushing down so that it's going to move down, and we get that rotation effect. So make sure you've got that sentence written down. If you want to do the sketches, you can, but it's not necessary if you don't want to. The sentence is the important part first of all. So I'll leave this up for about another minute just so you've got a chance to do that if you want to. Now, what we need for a motor to actually work is the ability to make that coil spin continuously. So that means that we need the current to be moving in on one side and out on the other continuously. We can't have a situation where it's going to be kind of flipping, because otherwise the motor wouldn't actually spin. So the way that we set this up so the current is always going in on one side and out on the other is through the use of this thing called a split ring commutator. Now, the picture at the bottom shows you what this looks like. It's called a split ring because it's basically a ring with a split in it. Pretty high tech there, as you can see. So what we've actually got is this ring of metal, and it's actually been divided into two semicircles basically. So we've got these gaps between the two halves. Now what we find is that we've actually got these little contacts onto our power supply that then come into contact with that split ring commutator, and then our circuit connects onto there. So that means that as it turns, it's always going to have the current flowing in on one side and out on the other, and it's going to be consistent with that. So write down those two sentences, and if you want to do the little sketch at the bottom, by all means feel free. I'll leave this up just for another minute or so you've got a chance to do that. Now, the reason the split ring commutator is important is because it allows the current to flow the same way from the battery, but change the halves of the coil as that coil is spinning within our magnetic field. Now, as we've said, this is really important to actually allow a motor to work, because it means then that the force on one side of the coil is always going to be in an upward direction, and the force on the other side would always be down. So for example, if we're looking at our coil, the force on the left hand side of it would always be up, and the force on the right hand side would always be downwards. Even as it's turning, then it's the left is always pushed up, the right is always pushed down. If it didn't have this, then all it would do, it just kind of vibrate backwards and forwards, not fully turning, because as we then got to that halfway point, it couldn't then go all the way around, because obviously at that point the current is going in the opposite direction, which means it's then going to flip back. So the split ring commutator allows the current to flow the same way from the battery, but change halves of the coil as it spins, so it will always be in that rotating form. Left hand side always up, right hand side always down, for example. So make sure you've got those two sentences written down. I'll just give you another 40 seconds to do that. So what I'd like you to do then is have a go at explaining how a motor works. So to help you out with this, I've given you 3 diagrams at the bottom, and they've got a little explanation underneath them. So what I want you to do is have a little read through those 3 different diagrams, look and see what's happening in the picture itself, and then in your own words, I want you to have a go at explaining how a motor works. So I'm going to give you about 4 minutes So have a good go writing this down in your books for me to explain how the motor works. Okay, hopefully what we've written down then is if we start with the diagram on the left hand side, so the first one in the sequence. Now what we've actually got there then, our coil has been divided up into the two colours, so we've got the purple colour on the left hand side and the orange colour on the right. Now what we can see is if we use Fleming's left hand rule, then our finger, first finger remember, points north to south, so you can line that up going from left to right on the screen as it were. Then your second finger is the current, and if we look, that's coming out towards us on the purple side. So that side, the left hand side, the purple side, is going to be pushed upwards because that's the direction your thumb is in. If we do the same thing with the orange side, so we still have north to south, left to right as our first finger, but if we look at the current this time, it's going into the screen. So flip your hand upside down And what we find is that the orange side is going to be pushed downwards. So that's our first bit, is that the purple side is going to be pushed upwards and the orange side is going to be pushed downwards. Then what we see is in our second picture, this is the point that it started to turn, and if you look at where our split ring commutator is, you can see that actually those little brushes that connect onto the actual device there, they're actually in the gaps between the two halves. So what we see at this point is there's no current, but the coil is going to continue to turn because of its own momentum. So at that point, because obviously those brushes are no longer connecting onto the split ring commutator for that point in time, we don't have a current flowing, but it still continues to turn. Then the other side, so our purple side, is going to come into contact with the brush on the right, and what we then see is we get the direction of the current in the coil and the commutator being reversed. So again, get Fleming's left-hand rule. So still going left to right with our first finger because the north and south haven't changed. And if we look at our purple side, so the purple is on the right now, our finger, second finger, has to point into the screen. So that means the purple side is being pushed downwards. And if we do the same for the orange on the left there, that's going to be being pushed upwards. So that means that our coil is still rotating in the same direction. So hopefully you got your explanation there. If not, then just add in any little bits that we've got. You can always pause and reverse the video just to go back over those points should you need to. Last thing we need to consider in today's lesson is how we can actually change the speed of a motor. Because obviously we don't want every motor to run just at one speed constantly. It's always useful to have motors that can run at different speeds. So in your books, I'd like to write down any ideas on how you've got as to how we could change the speed of a motor. So I'm just going to give you a little over 30 seconds to do that. So when it comes to changing the speed of the motor, there's 4 key things that we can do. So we can change the speed of our motor by changing the magnitude of the current, so the size of our current. We can change the strength of the magnetic field, and that basically means we're swapping out for stronger magnets or weaker magnets. The third one is we can change the number of coils in our wire. And the last one is we can change the length of the coil. So any of those 4 will get you marks if they ask you how you can change the speed of a motor. But if they ask you how to increase the speed of a motor, don't just write down the magnitude of the current. Obviously there, if we're asked how we could increase the speed of a motor, it would be increasing the size of the current. We'd obviously be talking about increasing the strength of the magnetic field, increasing the number of coils on the wire, increasing the length of the coil. So just read those questions carefully so you don't throw away a mark by just poorly phrasing your answer. If it just asks how you could change the speed, then you can literally write them as they are there. If it asks you how to increase the speed, then you've got to say how to make it go faster. So to finish off today then, those of you with target grades up to a 5 then answer the questions on the left. Those of you with target grades over that, then it's the questions on the right. So I'll leave this up here just for about a minute today. If you need longer, just hit pause on the video now. As always, you can find the answers to the plenary over on my website, sciencewright.weebly.com. You'll also be able to find that under the Internet tab. Just select the week that we're in, and then you'll be able to find things like the lesson PowerPoints, the answers to the plenary, any additional work, and if there's any little experiments I thought you could do at home, then they're there too. So have a look and get using that.